All right, you guys, welcome to Unit 4. Just to kind of give you a heads up about Unit 4. Unit 4 is kind of a hodgepodge of stuff in this unit, meaning we have a lot of topics in geometry that don't really belong necessarily in a particular unit as a whole overall topic. So we use Unit 4 to kind of put all these little mini topics. They're all related, of course, but they're not nearly as cohesive as the other units that we're going to be, that we've talked about or that we will talk about. So just letting you know. So I'm just going to go through these day one notes. We're going to be talking a lot about similar figures and proportionality. You learned pretty much all of this in elementary and middle school. So we're just going to kind of reiterate a lot of that old information and maybe step up a little bit on some of the problems. I do want to let you know that your homework today is super easy compared to the notes and some of the problems that we're going to be seeing today, but your homeworks tomorrow and the following day will have more and more and more challenging questions on them. So we're just kind of get all of them out of the way today in these notes, so that we can save some time later. I'm not going to lie, these notes are pretty lengthy. There's a lot going on and a lot of examples to go over. So I'm going to go through them as quickly as I can, and then feel free to pause, fast forward, rewind as needed. Okay. All right, here we go. So we're just going to go through some vocabulary that we need to know in order to start Unit 4. So a ratio, we all hopefully know what a ratio is, right? It's just when you compare two numbers, right? Two numbers that actually mean something. So for example, in this picture, notice the arrow. The arrow is kind of indicating the way they want us to compare. So notice we have this side length of 5, and notice that his corresponding side, remember that terminology, you're going to need that a lot in this unit, right? So his corresponding side, or the same side location, is a 10 on the other one. So if I'm comparing my smaller pentagon, technically, to the larger pentagon, then I might write a ratio of 5 to 10. Now remember, there's a few different ways you could write that. So you could say 5 to 10, right? And actually use the word 2. You could, I don't do that. You could use a colon, 5 to 10, right? But unfortunately, neither one of these scenarios is good for math problems. So we typically write our ratios as fractions, right? So any of these are technically viable ways to write a ratio, but fractions is going to be a kind of our go-to. Okay. Now, when I'm comparing two numbers, I can either say 5 to 10, I can say 10 to 5, unless it's indicated like exactly which way they want me to compare it, like what this arrow is doing, then either way is fine. Now, I say that with a grain of salt because our next word is scale factor. And scale factor is a very specific ratio that compares the new to the old, right? So in this case, right, and we always kind of read pictures from left to right. So like this is the old one, and then we did something to it to make it bigger. So now here's the new one, right? And we always compare new to old. So in this case, what is the scale factor of these two polygons, right? So if we do new to old, I'm just going to write this down, right? Our new length was 10 and our old length was 5. Right, so that would, and you should reduce when you're writing a scale factor. So 2 to 1 or just 2, right? Either one of those answers would be perfectly fine, right? But so if it just asks for the ratio, like, hey, compare any two sides you want, then 5 to 10, 10 to 5, who cares? But if it specifically asks for the scale factor, it has to be new compared to the old. Okay, so just be really careful with that. We'll be talking a lot more about scale factor later on in the unit as well. Okay. All right. A proportion is an equation that states two ratios are equal to one another. Right. So 2/3, for example, equals, well, let's see. I know 2/3 is equal to 4/6. Right. This is technically a proportion because I have written two fractions that are clearly equal to each other. Now, of course, for our purposes in math, typically there's a question, one of the numbers we don't know. Right. So we have math equations that would look like this, right? 2/3 is equal to what over 6, right? Still a proportion, but now you're solving for that missing value that makes the fractions equivalent. And clearly we know that x is 4, right? So we will be solving a ton of proportions in this unit. And I'm hoping you remember that the simplest way to solve a proportion is to cross multiply. Now, it's certainly not the only way to solve a proportion, but it's definitely going to be the easiest way. Some of your teachers in middle school might have called it the butterfly method, because when you cross multiply, it kind of looks like a butterfly. Anyway, so we're just going to solve this one super quick. Please remember the equal sign always stays in the middle, no matter which way you cross first. So it does not matter which way you cross multiply first. I'm just going to go ahead and multiply this direction first. So multiplying 31 times x, which gives me 31x. And then I need to multiply the other way and multiply 5 times 24.8, which is 124. Right, and then of course we just need to solve that equation by dividing by 31, and that's going to give us x equals 4. Okay. All right, moving on. Definition of similar. So we spent the entire unit 3 proving that triangles were congruent, which means completely identical in every single way, right? But similar doesn't mean the same thing, clearly, right? So similar is kind of a two-part statement. So whenever you see that things are similar, that means that the corresponding angles are congruent, right? So the angles are congruent. It's kind of like if we talk about we talked about this before, an equilateral triangle. Right? It doesn't matter how big or small, I make an equilateral triangle. Again, I'm saying these are equilateral, so that means all of our sides and angles are congruent, right? To be equilateral, that's an equilateral triangle. That's an equilateral triangle. And we know that all the angles of an equilateral triangle are 60 degrees. So it doesn't matter if he's tiny or large, right? The angles are still 60 degrees, right? And so all the corresponding angles have to be congruent. But of course, the corresponding sides are not congruent because one is larger than the other. But the corresponding sides do have to be proportional, right? Which is why we're going to be spending the next couple of days setting up tons and tons of proportions, right? And solving them so we can find missing sides of similar figures, okay? All right, so I just wanted to talk about how we properly write similarity statements. So we already did congruency statements in Unit 3, so this one shouldn't be that big of a stretch. So a similarity statement is, if I look at these two triangles right here, I can clearly see that all of their angles are congruent, all their corresponding angles are congruent, and I can prove that the corresponding sides are proportional. Here, let's actually do that first. Let's do what's called an extended proportion first, right? So what we need to do is we need to find all the corresponding sides. So for example, I know the 6 or length AB on that triangle is corresponding to the 9. So I can make a ratio out of that, right? So I'm going to say the ratio 6 to 9. Sorry, there's something on my screen. And then I can go find my other corresponding sides, so 4 to 6, and I can set up that ratio, 4 to 6. And then, sorry, I'm hunting for colors. There we go. I know that 3 corresponds to 4.5. And please notice I went the same direction every time. It doesn't really matter what direction you go, like we talked about just a second ago, right? But you do, when you're writing multiple proportions with the same figure, right? We want to make sure I chose to go little to big, right? And so that means all of my ratios need to be in the direction little to big, or little on top and the big on the bottom, okay? And then it's called an extended proportion because I can put equal signs between all of those. So it's not just a single proportion, like that's a proportion and that's a proportion, and I can put the beginning and end together and that's a proportion, or I can just write them all three at the same time, right? And I know these are all equal because if I were to reduce all of them, they all reduce to 2/3, right? And we can just test that in our calculator if we need to. Okay, so these are definitely similar figures because the corresponding angles are congruent and their corresponding sides are proportional, which means we can write a proportionality, or I'm sorry, a similarity statement, which basically says, oh, okay, well, it definitely matches that definition of similar that we just talked about right there. So I'm going to say that triangle ABC is similar to, and that's this symbol right here. Okay, so this is our similarity symbol. Notice it's just the tilde. It doesn't have the equal sign underneath it like the congruency symbol does. And I do need to make sure that I name the other triangle in the exact same corresponding order. So using your context clues, if I say triangle ABC, I have to name the other one triangle DEF. Okay. All right. So there's two very important properties of proportions that we need to know. The first one is the most important, clearly. It's called the cross product property. And this is the property that allows us to cross multiply, right? So if you were to look up anything that says cross product property, it says if A over B equals C over D, then we know that A times D has to equal B times C, right? So I can find their cross product or cross multiply, right? And I know that those two things must be equivalent. Okay, so this is the most important one, all right? This is the one we're going to be using for the next few days. The next one is called switching the means, and you actually don't need to know this, but I want to talk about just how you do proportions really quick. There's two different trains of thought of how people set up their proportions, and which one you choose, it does not matter to me whatsoever. Okay, so I'm going to give you an example really quick. All right. I'm just going to draw myself two little triangles over here. Copy. I'm going to shrink one down. There we go. There's his little similar buddy. Okay, so let's say I have, sorry. So I'm going to name my corresponding sides. I'm going to do like A is to B as C is to D, because that's kind of what this is saying. Right? This is saying that A on one triangle is compared to B on the other, right? And then C to D. Now, it doesn't have to be this way though, okay? So what I'm trying to say is when I do my proportions, I will always set up my proportions the same way. So I always like to go from one triangle to the next. And I say A on this triangle corresponds to B on the other, and then C corresponds to D, right? And that's where I get my ratio. A is to B as C is to D, okay? And that's what's written right here, right? That's normal, right? Now, you don't have to do yours that way, right? Some people like to do theirs like this. They're like, I'm going to take left side bottom of one triangle and make a ratio out of that. So they'll say A is to C, and then they'll do left side to bottom. So they're still doing corresponding sides, but they're writing a ratio for the big triangle on the left and then a ratio for the smaller triangle on the right. And they're doing A is to C as B is to D. Again, I do not do mine this way, but if you do, totally fine, because look what happens. Do you notice when you cross multiply, we're going to get C times B? Oh, look, C times B. And if I multiply this way, I get A times D. Oh, look there, A times D, right? So I'm going to end up getting the same cross product or the same cross multiplication answer with a totally different looking proportion or how that was set up, okay? So you don't have to know like the name of this, like switching the means property. You don't have to know any of that. I just wanted to bring it up because I want you to know that if you happen to set your proportions up differently than me, then that's okay, as long as you're consistent with your movement, right? Notice my arrows. If I go blue, oopsies, sorry about that, right? If I go left side is to bottom, I can't go bottom is to left side and reverse it. Right? So as long as you're consistent, left to right, or left to base, it doesn't matter. Okay? Just stay consistent. All right. I think I've totally overtalked that. So I'm just going to write be consistent, right? With your movements, right? All your arrows have to be starting and stopping in the same corresponding spot. All right. Let's go finally do some questions. Here we go. Find AC. Okay, so they're wanting us to find this length. If AB to AC is 15 to 8. Okay, notice they're giving it in colon format, right? So they're doing AB to AC. It does me no good to write it with colons, so I'm going to write it as a fraction. So AB is 60 and AC is 3D plus 2. all right? And they've told us that that ratio is 15 to 8. Again, it doesn't matter which one you write on the left or which one you put on the right, right? But I know everything about this triangle is going to be the ratio AB to AC. And I just filled all that in. And now we have this awesome proportion that we are going to solve by cross multiplying or finding its cross product. Sorry, I want to change colors. All right, so here we go. We can grab a calculator if you need it. I'm just going to cross this way first, right? So 60 times 8 is going to give me 480. Do I have room to put it over here? Yeah, I'm going to do that. I'm going to go over here if y'all don't mind. So 480 equals, now here's where you need to be really careful. This 3D plus 2 is a binomial, right? So you can either go ahead and distribute, or you just need to be aware that when you multiply the 3D plus 2 times 15, both terms have to get multiplied by the 15. So if you want to go ahead and distribute like as you're cross multiplying so you don't have to write the step twice, then that's totally fine, right? But I am going to have to distribute that. I'm going to get 45D plus 30. And now I just have a lovely two-step algebra equation to solve, right? So we're going to subtract the 30. And then we'll divide by 45. And that's going to give us D equals 10. Now, that's not my final answer, of course, because they wanted the length of AC. So that means we're going to take our D equals 10 and we're going to plug it in there, right? And so 3 times 10 is 30 plus 2, so that's going to give us 32. And if they were units, like inches or feet or something, we would definitely want to write those. But in this case, they didn't give us the units, so we'll just leave it as AC equals 32. All right, let's go look at number 2. Find the value of X. Okay, well, here's X. And let's see, his corresponding side is the 40. So we want to make sure that those go together. And it looks like we have tons of other numbers. So as long as you pick another pair of corresponding sides, I'm just going to go pick the 20 and the 16 because why not? Right, and so I'm going to use those 4 things to set up my proportion. Now again, I like to set up mine as like 40 is to X. Oops. Right, so I like to just go from one shape to the other. So 40 is to X as, now I started with the big shape, so I have to start with the big shape again and go this direction. As long as you're consistent, you can set up your proportion however you want to. If you want to do 40 is to 20 as X is to 16, that's fine too, right? That's probably a lot easier. You can actually like figure out X without actually doing any work. So I'm going to just do a quick little cross multiply and solve here. All right, so that's going to give us 20x, 40 times 16. This gives us 640. All right, and obviously when we divide by 20, we are going to get 32, which makes sense, right? Because 40 is double 20, so our missing side should be double the 16. And guys, just for a little heads up, I don't really care. I'm really proud of you if you can answer the question in your head, but you must set up a proportion and show me your solution, okay? Because they're not all going to be easy peasy, just plain old numbers like this guy, right? And so I need you to prove to me that you know the proper proportion that would be used to set up and solve the problem, right? If you can do it in your head, great. That's a great way for you to check your answer after you've shown all your work. But I need to know that you know how to set up the proper proportion that matches the picture, okay? That's really what the most important part right now. All right, let me put a box around that. There we go. Okay. Moving on. So now we're just going to solve similar triangles. We have quite a few examples to do here. I am going to go through every single one of them because they all have their own little specialness to them. I would suggest you pay attention to the majority of them. If you want to, you can pause the video and try to do them yourself and then fast forward the video to the end of the solution and see if you did it correctly. And if you did, well then great. Okay. Let's see. How tall is the flagpole? All right. Well, I'm going to put my X there because that's what they're asking me to find. And please notice that there are 2 triangles in this picture, right? We have this triangle right here that's being made by the guy. And what I would assume is his shadow, right? You guys have heard these questions before. Like here's the sun, right? It's shining down on the flagpole and it's making shadows on the ground, right? That kind of a thing. So it looks like the 6-foot tall guy is creating a 10-foot shadow, right? But then we also have Oh no. We also have this whole triangle, right, being created by the flagpole, right, and its shadow. Now, the thing that you have to be super careful about in this problem is this 12 right here. He is what I would refer to as a completely useless number. Well, he's not a useless number. We are going to use him. But all by himself, he cannot be used. And I hope you can see why, right? Because 12 is the length from here to here. And is that a full side length of any of the triangles in this picture? No. Right? So we want to make sure that we are never, ever using partial sides, right? And I'm going to write that in little capital letters here. No partial sides, right? You are not allowed to just use that 12 in your proportion at all, ever, right? Because he's a partial side and I need the full corresponding sides of the triangles. Okay, so here we go. I'm going to set this up. I'm going to do height is to height. So I'm going to do, I'll start with the man. So I'm just going to do 6 is to x. Again, you don't have to set your proportion up the same as I do. As long as our cross products are the same, then we're good. All right, so no partial sides. So I'm doing, you know what? Hold on. I'm going to kind of keep track for myself that I'm doing the man information on the top and then the flagpole information on the bottom. Right? So the man's height is 6. The flagpole's height is x, right? Then I'm going to do the man's shadow, right? So the man's shadow was 10. And what was the flag's shadow, right? The flag's shadow is 22, right? We need the entire length of the flag's shadow. So we need to add the 10 plus the 2 to get that full side length. Okay, do not use the 12. Not going to help you there. And that's it, right? Once you set it up, it's a really easy proportion to solve, right? Nothing too crazy. So let's give that a solve really quick. I'm just going to cross multiply. All right, so I'm just going to do the 10 times x. So 10x equals 132 when we multiply the 6 times the 22. And when we divide by 10, we get 13.2. I am going to put feet on the end of that because we always want to use units in real world examples if they're given to us in the problem. Okay. All right, moving on. Number 3, solve for x and y. All right, so I do want to point out that we have a lot of parallel lines here, right? And the only reason why that's important is because that actually does prove that these are similar triangles, which we will talk about tomorrow. So here we go. I'm going to solve for x first, and his corresponding side is 6. Now, obviously, I don't want a proportion with an x and a y in it, and the y corresponds to 10, so I'm not going to use him. I'm going to have to use the 12 and the 15, right? So x is to 6 as 15 is to 12. Again, I don't care what order you put them in as long as you're consistent. X is to 6, 15 to 12. Notice my arrows. I'm going big to small, right? Or you can do small to big, right? Or you can do the switching of the means thing that I was talking about earlier. All right, so here we go. I'm just going to do a quick little cross multiply. So we're going to get 12x, right? So 12x equals 90. Right, and divide that by 12, and we're going to get 7.5. All right, I'm going to scooch that over and enlarge that just a little bit. There we go. Then we're going to go solve for y. Well, y corresponds, I'll do 10 is to y, so I'm still keeping that big to small, so I'm going this way. Now, you can use the 7.5 if you want, since we just solved for x, but I would highly suggest that you don't use previous answers and plug them back in to find other stuff unless you absolutely have to, just in case you did something wrong and got that x incorrect. We don't want it to affect our y. So I'm going to use that 15 to 12 ratio again. Okay, so 10 is to y as 15 is to 12. Erase my arrows. All right, that's going to give us 15y equals 120. Right, so we're going to divide the 120 by 15, and we get a nice even 8. And that makes sense, right? We know it has to be bigger than or less than 10, right? Because it's a smaller triangle. All right, number 4 is a tad tricky because, and we just talked about this in Unit 3, so I'm hoping we catch on. This is a rotation of itself, and so you need to be really careful because a lot of people might naturally think that the 6 corresponds with the 9, but it does not, right? Remember, this is a rotation. I would highly suggest that if you struggle with that, start putting some context clues in the picture for you. Like, does everybody notice the parallel lines here? Notice the Z-shaped pattern. So I know this angle is congruent to this one. Or I can do my backwards Z, and I see some alternate interior angles here and here. And then, of course, we have our good old vertical angles, right? So if you need to, go ahead and put those congruent angle things in there, because you notice then that I can totally see that the 6 is the side that's between my single arcs and my triple arcs. So he must correspond to the Y, because Y on the other triangle is between the single arc and the triple arcs, right? So put those context clues in there for yourself so that you're like, oh yeah, this is a rotation, and the 6 actually corresponds to the Y. The 5 corresponds to the 9, right? And the X clearly corresponds to the 18. So again, it's a very simple, oh, I should have just switched colors there. Thought I did, sorry about that. Right? So it's a pretty simple problem. It's just like the previous one, very easy proportion, but if you don't know how to, if you can't see that rotation, it's going to be tough. I'm going to go ahead and solve for X first, and I'm just going to do little to big. So I'm doing top to bottom, right? So X is to 18. And then, of course, I'm going to pick the 6 to 9, right? Because I don't want to, obviously, my other ratio would give me a Y, and I don't want an X and a Y in the same problem, right? So 18 times 6 gives us 108. Multiply the other way, we get 9x, right? And that's going to give us 12. Now, again, I knew that was going to be 12 5 minutes ago because obviously, hold on just one second. Oof, right? Well, we'll talk about that later. All right, I'm going to go solve for y really quick. So I'm just going to go top to bottom again, right? So I'm just going to 6 this to y. Did I just set that? Hold on. I totally did that backwards, y'all. Goodness gracious. Erase. I'm so sorry. I don't even know what I was thinking. I knew that answer was wrong, and I was like, what is happening? All right. Oh, my goodness. I just totally did what I told you not to do. Let's start over. Here we go. So x is to 18, right? So my purple guys. And then I need to use my 5 is to 9. It's like I talked about it, and then I made myself just subconsciously do that. Okay. So x is to 18. As the 5 is to the 9. There we go. That is so much better. All right, so we're going to get 9x, right? And then we'll multiply our 18 times 5, and we get 90. So x equals 10. That makes more sense. There we go. So sorry about that, you guys. And then now I can actually solve for y appropriately, right? So I know 6 is to y. And I'm going to go ahead and use that 5 is to 9 again. All right, so 6 is to y as 5 is to 9. Cross multiply, right? So we're going to get 5y equals 54. Divide that by 5, and we're going to get 10.8. Right? And I'm totally fine with that decimal answer because it's finite. Right, it's exactly 10.8. If you want to convert that to a decimal and write it as 54 fifths, like as you see right there, then that's totally fine too. All right, stepping it up just a notch here on these last couple. All right, so notice once again, we also, the big problem is we have, I'm going to highlight my sides here. So we have 11, and he clearly corresponds to the 7, right? So that is not the issue. Let me go ahead and start setting up my proportion here. There we go. All right, so I know the 11 corresponds to the 7. Now, I'm going to scooch this over just really quick, sorry. And I'm going to note that the 11 is the big triangle, and the 7 is the small one, because I want to make sure that I don't mess that up. And I have to do big to small to big to small, right? I can't do big to small, small to big. That's not consistent movement, okay? So now, if I'm doing big to small, let's go to the other side that was given to us, all right? So big would be this whole side, right? Please remember, this x is useless to me as just an x because he's a partial side of that triangle. So in order to get the whole thing, we're going to use the good old segment addition postulate from the very first week of our class, right? And so clearly this whole thing is x plus 15. And that is what's going to go up here. And then, of course, the small side of the small triangle is 15. So 11 is to 7 as x plus 15 is to 15. Big is to small as big is to small. Okay, so again, I'm going to put a little note here. No partial sides, right? You should not have this plain old x floating around by itself in the proportion. Okay. All right, and once you got it set up, it should be pretty quick there, right? So let's see. I'm just going to cross this way first. So don't forget I have a binomial, which means I'm going to have to distribute that 7. So 7x plus 15 times 7 is 105. All right, then I'm going to do 11 times the 15, which gives us 165. And there's our nice little two-step algebra equation. All right, so we're going to subtract the 105, get 7x equals 60. And we're going to divide that by 7. Now, when I type that in my calculator, that is not a friendly answer, right, or a friendly decimal. It does keep going on forever. So I'm just going to leave my answer as 67ths. And that is the most reduced. You can hit math, enter on your calculator, and it'll take you right back to that 67ths. All right, and that is okay. All right. Let's see. All right, we're going to do just a couple more. Sorry, give me 1 second. Okay. All right, how many more we got? Oh, 2 more. Then we're going to talk about a really strange topic, but a useful one later on. All right, so here we have 2 triangles. Again, please notice we have the little guy, right? And then we have the whole big triangle, right? So we see this fairly often where the smaller similar figure is contained within the larger one, very similar to that one that we just did, and also that flagpole question, right? So that's going to be pretty normal for us. So here we go. I'm going to highlight my corresponding sides. Now, in this one, I'm going to choose to do small over big. And just kind of make that decision and just write it down, or just kind of make sure you just don't forget which triangle you're starting with. So I'm going to compare my small to the big. So here we go. We're on the left side. So my small is 3, but he corresponds to this side of the big triangle. And we need to figure out what that whole side is, because I can't use x minus 2 by itself because that's a partial side. So I need to add the 3 plus x minus 2, which is going to give us x plus 1 as the full side length by just adding those 2 segments together. So I'm going to do 3 is to x plus 1. Then I'm going to go to the other side and do the same thing. So on the other side, I have x, which is the full side of a triangle, the small one, so x. And then I need the full side length of the big triangle, which means I need to add the 2 pieces together. So x plus 8 is going to give me 2x plus 8. And that's what's going to go over here. Remember, no partial sides, right? So small is to big as small is to big. And there is our lovely proportion. Now I'm hoping you might see right away that this one's a tad bit more challenging or lengthy. It's not that difficult, but it is definitely a lengthier problem, because when I cross multiply this way, I get x times x plus 1. I'm going to go ahead and just write that out so I don't lose anybody. All right, so when we cross multiply this way, we have to multiply x times x plus 1. And then when I cross multiply this way, I have to get 3 times 2x plus 8. So a lot of distributing happening here. And notice, of course, when I distribute on this first one, oh my goodness, a quadratic. So I get x squared plus x. And then I cross multiply, distribute this way. So 6x plus 24. Right? And as soon as you distribute, you're like, oh man, it's a quadratic. So we're going to have to solve it as a quadratic, which means we've done this dozens of times, right? That means we have to get it set equal to 0. So I don't know about you, but I am going to subtract my 6x. You always want to keep your x squared positive, always. It's so much easier to factor when your x squared term is positive. So we're going to subtract the 6x and subtract the 24 over to the other side so that we can get this sucker set equal to 0. So x squared minus 5x, because we've got to add it with that 1x, minus 24 equals 0. Luckily, it's a pretty simple quadratic because there is no a in the front, so you can just hop right to your factors. You don't have to do factoring by grouping. I'm looking for the only two numbers in the world that multiply to give me negative 24, but add to give me negative 5, right? And that's going to be negative 8 and positive 3. So there's my factors. You can, of course, go to your calculator and have it help you out with that if you need to, right? But we're not done because we still have to set our factors equal to 0 and then solve these little equations. So we get x equals 8 and x equals negative 3. But remember, we're in geometry class, so we need to figure out if we can actually use both of these numbers. And the one that should cause us pause is the negative 3. And notice that's going to be a problem because if I plug that negative 3 in here or here, it's going to give me a negative number. It only has to fail in one spot. So it definitely cannot be 3. So that answer is void, and the x equals 8 is going to be good to go. And you can, of course, plug the x equals 8 in, right? These are completely checkable, as are most questions in our class, right? So you can totally plug that in and just check your final answer if you need to. All right. Let's see. Is that going to move everything? No. Sorry, I was trying to scooch this up just a bit so it's not smack dab with our other problem. Okay. Our last one of these, number 7. So again, notice the parallel lines, right? We should always be noticing the parallel lines. So the first thing, I don't know about you, but the first thing that jumps out at me is transversals, right? So if I make this transversal, notice the Z shape, then of course that means X has to equal, you know it, 74. So I'm going to go ahead and put that in there. I also know that I can use the other transversal, right? Which means that the Z is alternate interior to the 48. And I can solve for Y because I know triangles have to add up to 180. So hold on, let me write this. I'm going to put 74 right here. Right? So I know Y has to be what's left over from the 180 degrees that every triangle has. I'm going to type that in my calculator. 180 minus 48 minus 74. Oops, I did a double negative. Sorry. Minus 74. Delete. There we go. And I'm getting 58 degrees for Y. Okay. Now, V and W, right, those are the only things that we have left. V and W, though, are side lengths, okay, not angle measurements. So we're going to have to set up a proportion to solve for those, right? And again, use your context clues. I'm going to unhighlight all this if everyone's okay with that. It's kind of busy. So I'm going to highlight our corresponding sides. So clearly I know the 40 and the 32 correspond, but remember these are rotations of each other. So the 30 corresponds to the W, right? Use your context clues, right? Look at your angles. And then I know that the 35 corresponds to the V. So once everything's kind of nice and highlighted, I can set up a very quick little proportion here. So I know 40 is to 32. So I'm clearly doing big to little, right? I'm going top to bottom. So if I do 40 is to 32, then I'm going to do, let me change colors, 35 is to V. So 40 is to 32, as 35 is to V, all my little corresponding parts there. Let's see, let me get my calculator. 32 times 30, oops, 32 times 35 is 1120. And that's 40V. And then we're going to divide that by 40. And I'm getting 28. I hope you got the same thing. All right, so our V is 28. And then I need to solve for the last variable, which is that W, right? And so I'm still going to go ahead and use the 40 over 32 again. So I'm still going top to bottom. But now that I want to solve for W, it's going to be 30 is to W. All right, and then I should be able to cross multiply. So I'm going to get 40W. Let's see, 32 times 30. I already know what that is. I don't know why I'm typing that in. 960. And then dividing that by 40. So I'm getting 24 for W. Okay. Just filling in a lot of missing pieces. All right, awesome. The very last thing I want to talk about is geometric mean. All right, this is one of those topics. It's actually super easy, but I'm going to probably overcomplicate it because I want you to actually understand what it means and where it comes from. No pun intended. So we're going to be talking about geometric mean also when we get to Unit 5, right? So it's going to come back to us here in just a few short weeks. But we're just going to introduce it today. Okay, so when you guys hear the word mean, you probably think average, and that's exactly what that means. However, there are a lot of different types of averages in the world. You guys are used to the arithmetic mean, right? And yes, it's pronounced arithmetic. You can say arithmetic if you want, but when we use it as an adjective, we pronounce it arithmetic. So you guys are used to the arithmetic mean, which means to add and divide by how many things you have. Like if you find a test average or what have you, right? But a geometric mean is not the same thing. It's still an average per se, but it's not the same kind of calculated average. So here's what it means. A geometric mean basically means if I want to find the geometric mean between 25 and 4, what I'm actually thinking about is what is the area of a rectangle whose dimensions are 25 by 4. Well, we all know, hopefully, that the area of a rectangle is base times height. So the area of this guy would be 100 square feet, right? So what we actually are talking about when we do geometric mean is what would the side length of a square have to be in order to have the same area as that rectangle that was 4 by 25? Well, the rectangle had an area of 100 square feet, and so does this square. So what would the side lengths, let me put little question marks instead of X's, right? What would the side lengths of the square have to be to also give you an area of 100? Well, obviously, you're asking yourself what number times itself gives you 100 because it's a square, and hopefully you're all shouting 10, right? And that, guys, that's the answer. So we would say that 10 is the geometric mean of 4 and 25 because 10 is the side length of the square that would have the same area as the rectangle with those dimensions. Isn't that weird? It's kind of crazy. Do you notice how 10 is a number between 4 and 25? But it's not the arithmetic mean, right? It's the geometric mean, okay? All right, so let's go, just do a couple more really quick. So what is the geometric mean of 7 and 28? Well, I don't know. Let's see. The first thing that we're going to do is we're going to calculate, and you don't have to actually draw anything out, right? So if I had a 7 by 28 rectangle, right, then he would have an area of 196. So then you're asking yourself, what would the side length of a 196 square have to be? So you're asking yourself what number times itself gives you 196. And it is a perfect square, and that is 14. So that is the geometric mean of 7 and 28. And notice it is a number that's somewhere in between 7 and 28. It's not smack dab in the middle because it's the geometric mean and not the arithmetic one. Isn't that interesting? Again, I don't expect you to draw this picture every time because we're doing the same 2 steps every time. So let's kind of think about this question right here as we do this next one. What is your thought process, right? How are we actually calculating this so we don't have to sit here and draw a bunch of rectangles and squares every time, right? So if I want to know the geometric mean between 8 and 4, okay, well, what am I going to do? I'm going to multiply 8 times 4. I'm just going to do that over here if everyone's cool with that. So we know 8 times 4 is 32. And then we want to know what number multiplies by itself to get 32. Well, technically, when you ask yourself that question, you're finding the square root of 32, which of course why we call them square roots, because they're side lengths of squares. Okay, does that make sense, everybody? So the square root of 32 is not a perfect square, but we know how to simplify radicals, and we always should, right? So that's 16 times 2, and 16 breaks down into 4 times 4. I'm just going to stop there, even though I know 4 isn't prime. But once you find a pair, you can stop. You don't have to keep going because I know that's just going to give me 2 times 2 times 2 times 2. So I'm taking out 2 2's, which is the same thing as a 4. So I'm just going to stop at the 4's and just say, okay, well then my geometric mean is 4 root 2. Okay. So how are we calculating this? Number 1, we multiply. And then step 2, we square root. Right? That's literally the only 2 steps to calculate the geometric mean. Now, why are we talking about this? Well, because geometric mean is technically a proportion, right? I don't know if anybody's heard this before, but when you set up a proportion, you actually, the position of the numbers in your proportion, they have specific names. I'm never going to quiz you on this or anything, but I just want to let you know. The lower left and top right numbers, those are called the means. Right? So if I'm calculating the geometric mean, then I'm going to put an X at the bottom and the top right because I am looking for the geometric mean. Then the top left, bottom right, those are called the extremes. And those are the 2 numbers that we know because they're the lowest extreme and the highest extreme. Right? And so all geometric means problems can be solved as a proportion. And notice what happens when you cross multiply this said proportion. Do you notice how we get x squared equals a times b? There's your multiplication step, a times b. And then how do I solve for x when it's squared? I square root. Right? And so that's why we're talking about geometric mean, because it can be found by setting up a proportion. And this is our unit of proportions. Okay. All right. 2 really quick, but we're going to solve these using proportions, which is how I want you to do them, right? You have to get used to anytime you see the word geometric mean, you should automatically be like, oh, that's a proportion. I know you can solve it kind of in your head or like we were doing up here, but I want you to get used to setting it up as a proportion because when we get to unit 5, right, you're really going to want to set it up that way because it gets a little more complicated. So I'm looking for the geometric mean. So I'm going to put my x's here and here because those are the means positions. And then my 3 and my 15 go in the extremes positions. And it does not matter, of course, if you put the 15 on top or the 3 because you're just going to cross product it anyway. So this is going to give us x squared equals 45. And then we just need to square root. I'll go ahead and just write this interim step here. So we know x is the square root of 45, which is going to give us 3 root 5, right? If you need to, you could do your little factor tree off to the side, right? So we know that's 9 times 5. 5 is prime, but 9 is where we get that pair of 3's. Okay. Now, technically, x squareds have 2 solutions, a positive and a negative root. But remember, we can't use the negative root here because we're looking for a number somewhere between positive 3 and positive 15. So we only want the positive root. All right, one more just really quick. Find the geometric mean. Ooh, I'm going to stop right there so I can set up a proportion. I'm going to put my x's here and here. And then, of course, we're looking for the geometric mean of 5 and 44. So we're going to throw that in the mix. When we cross multiply, we're going to get x squared. Oh, sorry, my calculator's about to die. 5 times 44, so 220. And so x is going to be the square root of 220. If you don't know your perfect squares, I would totally type that in my calculator just to see if it was, but it's not. So I'm going to go off to the side and I'm going to do 220. Now, just a little heads up, you can use any numbers you want that you multiply to give you 220. But if I were you, like, look, we already know 5 and 44. Like, let the problem help you out, right? I multiplied a 5 and a 44 in the first place to get 220. So I'm just going to go ahead and use those numbers to break it down again. And because 5 is prime and 44 just breaks down into 4 times 11. 11 is also prime. So the only number I'm getting any pairs out of is that 4. So I have a pair of 2s that I can take out. So my final answer, right, is going to be 2 root, and then the 5 and 11 have to stay inside. They get multiplied back together, and voila, the geometric mean of 5 and 44. Oh my goodness, thanks for sticking with me, you guys. I know that was a lot of notes. Your homework, like I said, is much quicker and easier than some of these questions, but we'll get to some harder ones on tomorrow's homework. So we kind of have a head start, which is awesome. All right, feel free to come in for tutorials if you have any issues with these notes or your homework, and I will see you guys later.